Hi everyone, welcome to the last episode of Math 261. This is Scott. Let's get started. So, today, the last section that we will be considering in this course is section 6.6, in which we will be looking at applications to linear models, and for some reason your book also calls this machine learning, which is, I think, a bit of a stretch, but put quotes on it. Alright, so here's the basic setup and then the basic idea. So the setup is, we are going to have a collection of data that it is our job to try to model. So setup. We have a collection of data values. Usually it'll be just x, y, but every once in a while we'll be talking about a situation in which there are more coordinates. So let's just keep it vague. We have a collection of data values and a model for which we need to fit the coefficients. Okay, so we already have an idea of what sort of model we want. That's an important part of this. You have to already have a style of formula that you're planning on using. And then if you do, then you have that, then what you can do is then find the values of the coefficients that will fit this best according to least squares regression. So then the idea is we can set up a least squares problem. And the format of this will be capital X times beta is equal to y. So the y here is a vector. We have capital X and we have beta, where X, which is called the design matrix, so X the design matrix, which we'll discuss how to set that up in a second. Beta, so this is called the parameter vector. And this one we can already actually set up, so it's equal to beta naught up to beta, and let's say n, where these are the missing coefficients that we know that we need, but we don't know the values of. So these are the coefficients in the model. And then y, this is what's called the observation vector. And in particular, y is going to be made up of the y values, so y1 up to yk, where these are the y values in the data set. These are the the data set. Now, every once in a while, letters will be different. We may not use y necessarily to represent the output. In statistics terms, this would be what's called the response variable, whereas the x will correspond to what's called the explanatory variable. Okay, so now setting up x. So this is the only part that really is going to be up for grabs here. So setting up the design matrix. So essentially what you need to do is you just need to use your given data values and peel off what are going to be the weights of each of the beta values, and those will serve as the entries along each row of x. So for each data value or data point, the coefficients of the beta values will comprise that row of x. So the usual case, so the most basic case, is linear regression. So the basic case, this is linear regression, where we're just finding a line so the basic case here we have x1, y1, up to xk, yk, and then the beta, so the model here will be y hat, so this is the way we typically write it, is with a hat. Y hat is equal to beta naught plus beta 1 times x. And so these are the unknown betas, which means that the parameter vector will just be beta naught beta 1, and the design matrix will be, you just take the coefficients, and for each coefficient the linear term is going to be it's just going to have a 1, and then it's just going to be 1, x2, 1, x3, and then you just get down to the last one, 1, x4. So it'll just have as many rows as it has as we have data points, and then the observation vector will equal then just y1 down to yk. So this is the most basic of all possible cases, where we are just talking about a straight line that we are trying to fit through the data values. Now, as we know, not all data values will necessarily lie on a line, and so this system of linear equations that we might be setting up may in fact be inconsistent. However, that's not the game anymore. The game is a least squares problem, so the goal will be to find the closest solution there is, and that will be the least squares regression line. Before we do any more, before we do an example of this, let's just discuss some more advanced cases. So this was the most basic case. Some more advanced cases. So we could say like polynomial regression. Would be a more advanced case that we could be dealing with. And in polynomial regression, here what we would have is again the data values, which we can write the same way. It's going to be x1, y1, dot dot dot, up to xk, yk. And a model will be, and then we would have to decide in advance what we want the power, what the degree of the model to be. But we could say, so let's say degree p. So then y hat could equal beta naught plus beta 1 x plus up to beta p x to the p. Then what that means is we have as our parameter matrix, or parameter vector, beta. We have these, beta naught, all the way up to beta p. So in other words, you just always get one entry for each of the unknown coefficients here, the betas. And then the design matrix now is going to be slightly different. You just read off what the coefficients are going to be. So just going to, and for each of the data values, it'll be 1 on the constant. It'll be just x1 on the beta 1, x2 squared, so x1 squared, I should say, x1 squared, dot dot dot, all the way until you get to the last one, xk to the p. And then the next one will be 1, x2 squared, dot dot dot, up to x2, to x1, 1 to the p, and then x2 to the p. And then down until you get to xk squared, dot dot dot, and we have xk to the p. So so each row is devoted to a specific data value, data point, so a specific x, and it just goes up in powers. And then the y vector, which is the observation vector. This will just be the same old one that it always is. So this is actually very similar. The only difference is in the design matrix. So the design matrix is what will be constantly changing throughout this. So polynomial regression or other types of functions. And let's take as an example, say something like, for example, y hat equals a plus b sine x plus c cosine x. So it doesn't have to be the slightest bit of a linear function, provided that the unknowns each serve as a coefficient of some specific term. Then here the beta is just going to be the 3 pieces, and we can even just write them as a, b, and c if we want, so as to help us customize this to our specific example. So the beta parameter vector will be a, b, c. The design matrix will be 1 for the coefficient of the a, the weight of the a. This will be sine x1. This will be cosine x1. So you'll just be taking the data value x1 and then just plugging it into sine and cosine to get the weights that will be applied to each of the parameters. So 1 sine x2 cosine x2 dot 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 down to 1 sine xk, cosine xk. And then here the observation vector will be just like it has been. y1 up to yk. So note, all that changes in each of these scenarios is the design matrix is what changes. So we can actually recycle a lot of the reasoning that we use in each case and and apply the same sort of reasoning each time. So note, in each of these cases, only the format of the design matrix varies. Now, solving these problems. Solving these regression problems. So no matter what situation we're in, we're always going to be dealing with x times beta equals y, which will be a system of equations, but it won't necessarily be a system of equations that is consistent. And in fact, usually it won't be. So here, what we can do is we can set up the normal equations. So make the normal equations x transpose x times beta is equal to x transpose y. Then if we solve these, then what we will get is the beta hat, which will produce the projection of the matrix, projection onto the column space of x, which will then be giving us the least fit model. So then, solving this gives beta hat which gives us our model y hat. Now, the way your book often words this is that this then allows a machine which has learned the model to then predict values for the output given values of the input. So this model would allow us or any machine that has learned it to predict y values for given x values, for given input values. So this process is only appropriate for input values. And the same approximate range as the given data values. Otherwise, it is called extrapolation. So we should be sticking to predictions that are in the same general genre of values as the x values. So if your x values are things like 1, 1.5, 1.7, 2, 2.3, then it wouldn't make sense to plug in an x value of 100 and expect a sensible result. Usually, the columns of x will be linearly independent allowing us to solve the normal equations by, so if you remember, we can solve it if we take the normal equation here, and if x has linearly independent columns, then x transpose x will be invertible, so we can cancel that out, and we'll have x transpose x inverse x transpose times y. Okay. Now this is a thing that is ungainly to do by hand as a human, but calculators and other calculating devices are capable of doing it without too much trouble, and so we will frequently, and in fact in all examples in this, we will be deferring to our calculators for the grunt work. But let's actually try doing this and get a feel for it. So an example here. So here's going to be our data set. The data set. I'm going to take 4 points, 0, 1, 1, 6, 2, 4, and 3, 7. That's our data set, and we're going to subject it to various amounts of analysis here. So first off, what we're going to do is we are going to try to find a least squares line through this data set. So 1a. Find a regression line not through exactly 4 this data. So in other words, we're talking about a line, so that means that y will be of the form beta naught plus beta 1 x. Okay, well then what that means is, so the parameter vector will be just of the form beta naught beta 1. Now the design matrix here is going to be the weights on each of the betas, and there are going to be 4 of them. So the very first weight on beta naught, so it's going to be 1 because it's just a constant. And then beta 1, it's going to be the corresponding x values. So it's going to be 0, 1, 2, and 3. These are the x values. And then as for the y, this is going to be equal to just the y values. 1, 6, 4, 7. So very easy to set up, especially for something as stereotyped as linear regression. Okay, well then, beta hat is going to equal x transpose x inverse, times x transpose times y, which actually we can just go ahead and put into our calculator. So here's the calculator. Now it can be a little picky about what letters are reserved and what letters are not, so I'm going to use D for design matrix, and I'm going to use O for observation matrix, because X's and Y's are pretty special in the calculator's mind. So here I am, just going through the motions here of entering in the things for X. And then 1, 3. Okay, so this will be my design matrix. So I will store that as D. Okay. So there's my design matrix D. And now for the observation vector, I'm gonna just see what I can do to save myself unnecessary keystrokes here. Okay, so I've got 1, 6, 4, 7. And that I will be storing as alpha O. Figure out where I can move this so there's no glare. Okay, there. So there's that. Alright, and now all I need to do is calculate this according to the method there. Almost always, by the way, in these, the design matrix is going to have linearly independent columns, which gives us this road to a solution. If, however, we had one that did not have that, we would have to do a row reduction. So as long as we have linearly independent columns, we can just use this little formula, and that will almost always be the case in these. So my calculator actually is perfectly happy to take inverses by raising to the -1. I didn't tell you that before, but now I will. You can do multiplication, you can do the times, and then math, matrix, transpose times, and then observation. Okay, so there is that. And I hit enter, and I get this. So it's 21/10 and 8/5, which these, because what we're talking about a very statistics heavy topic, it would be common also to express these as decimals. And in this case, it wouldn't even be approximate, it'd be exactly 2.1 and 1.6. Okay, so those would be the two parameters for the model. So that means then my regression line is equal to y equals, so it's going to be 2.1 plus 1.6x. Now what does that mean? So B. So for example, then if I wanted to predict the value that y would have if x equaled 4, something not quite in our data set but close to it, then I could just plug that in. So let's say, so the way your book words this is something like, if a machine learns this model. Let me zoom back out a little bit. I zoomed in for the calculator. Yeah. What? There it goes. So what would it predict? For x equals 4. So this is a slight extrapolation, but it's pretty close, and so it would be a perfectly appropriate use of this. So then, the predicted y value, which we can write with a y hat, which serves so many purposes, is 2.1 plus 1.6 times 4, which would then equal whatever that would equal. So that'd be according to my calculations, 8.5. Now this was a linear model for a set that was not actually ultimately exactly linear, so we may want to know how far off it is within its own specific scope. So if the machine predicts the y value for x equals, let's say, 3, how far? How far off? Would that be from the given data point? Well, let's see. So if y hat equals 2.1 plus 1.6 times 3, so then that would be equal to, I believe, 6.9. That would equal 6.9. Now the y value when x actually equaled 3 was 7. So the distance y minus y hat would be 7 minus 6.9, which would equal just 0.1. So very close at that data value. Now it wouldn't be so close at other data values, but that one, it would be very close. Now, let's take that same data set and subject it to a different model. So use quadratic regression to find a model y equals, so y hat equals beta naught plus beta 1 x, and here's what makes it quadratic, plus beta 2 x squared for the same data. Okay, now some things will be the same, some things will be different. In particular, the parameter matrix, now we have three parameters to fill in. We have beta naught, beta 1, and beta 2. And that's what we're here to find. Alright, and then as for the design matrix, now we're still going to have the 4 rows for the 4 data points. Now these are going to be basically the weights on beta naught. And then here we have the weights on beta 1, which are the x values. So 0, 1, 2, 3. So these are the x values. And then here what we have are 1, 6, we have 0, 1, 4, and 9. Sorry, I was looking at the wrong thing. 0, 1, 4, and 9. And these are going to be the weights that are going to be applied to beta 2, which are x squared. Okay, then as for y, that just is still the same old 1, 6, 4, 7. Alright, well, now beta hat is not actually any different in its calculation from what it was before. It's just that x is different and beta is different. But it's still going to be x transpose x inverse x transpose y, which again we can just go straight to the calculator and ask it what it thinks the answer is, because after all, it's willing to do the grunt work on this more reliably than we can do, provided of course that we don't give it any typos. Now here, in entering this, we'll zoom in a bit and get ourselves a closer look. So here, the easiest thing for me to do will be to just go back up to wherever the last time I entered a D was. So up here, if I just hit enter, then I can just go in and make modifications. Now notice it dropped my semicolons and changed it to its preferred format, but this is the first row, second row, third row, fourth row. So I'll just add in the extra piece that I need, which is a 0, which is a 1, which is a 4, and which is a 9. Okay, so now hit enter, and hopefully what I get should be the one I want. Looks good to me. Alright, now what I'm calculating is no different from what I calculated before as far as the letters, so I'll just go up to it, select it, and I should now get my new answer, which is going to be 8/5, 31/10, and -1/2. So now there are three entries because there were 3 parameters that needed to be filled in to specify a quadratic. So these are the ones I said, and then if I want to make it a decimal, which is a little bit more usual in something like this, just because it's something so data oriented. It's unusual for it to be an exact fraction like this. So then we can do that, which means then that y hat would be 1.6 plus 3.1x minus 0.5x squared. So this will be our quadratic model that we think would best fit this data. And so then if I wanted to use this, let's say to predict a value, so use this, let's say b, use this to predict y value for x equals 4, just the same prediction as before. We would just plug it in. And so you can just ask your calculator what that would be. 1.6 plus 3.1 times 4 minus 0.5 times 4 squared. And I get 6. All right. Now, let's interrupt this problem for a second to make a note. Note. When you use p plus 1 data values with distinct x coordinates, to find a degree p polynomial the polynomial will match the data exactly, and this will be, in this process, is called polynomial interpolation. Oops. Interpolation. Alright, so just as an example, let's just take that same data and find the degree 3 polynomial that would interpolate it. To find the degree 3 polynomial, what fits it best. In other words, the interpolated polynomial. So y hat is equal to beta naught plus beta 1x plus beta 2 x squared plus beta 3 x cubed. So it's just the cubic of the same basic format as the rest of them. So once again, here we have got a beta that is just going to be the list of the unknown parameters. So beta naught, beta 1, beta 2, beta 3. And then the design matrix now is going to be 1, 1, 1, 1. So these all represent the weights of beta naught. And then we have the x values of 0, 1, 2, 3. And then we have 0, 1, 4, 9. So these are the x values. These are x squared. And then lastly we have 0, 1, 8, 27. X cubed. And then the y's are the same as they were, which was 1, 6, 4, 7. So the only change, once again, is to the design matrix, but nothing else changes actually in the process here that we're going to use, which is x transpose x inverse x transpose y, and we just go again to the calculator, and again I'm going to recycle my earlier matrix in order to save myself a bit of the work here and save you some of the watching. So Make sure you clear out the line you're on, otherwise it ends up putting it just right after whatever was currently there. Second and left scrolls you all the way to the beginning, by the way. And I'm just going to put in the extra bit where there are the cubes of the x's. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. So that's my new design matrix, but the y is still the same, so we still have the same observation matrix, and so I can now just scroll up to the last time. What did I say? Don't forget to cancel that out. So I can scroll back up to the last time I calculated this and go ahead and find it again. So this works provided that the columns of the x will be linearly independent, which they will typically be in these problems. So this will be 1/25 over 2. So just recording down here what my calculator told me. -19 over 2. And then 2. In other words, if I put it into decimal 1, 12.5, -9.5, and then 2. So that means then my cubic model here is just 1 plus 12.5x minus 9.5x squared plus 2x cubed. Now this model will in fact be exact for all the x values, but I'm not going to belabor that too much. But notice that the x, so the design matrices here, the x matrix, has been building out in a very steady, very predictable format, and it is what is called actually the Vandermonde matrix, but that's not really so important for us to write down right now. It's not a key takeaway from this. It's just what it's called. But it will always have linearly independent columns, and so we will always be able to just use this formula defined to the b. All right. Now 4. So let's say we wanted a different kind of model, not a polynomial model at all, but a model that would give us maybe something like a periodic solution to this. So maybe what we will have is a model of this form. So use the same data set. Find a model of the form y equals a plus b sine x plus c cosine x. All right, well, then the beta here would be ABC. The design matrix will be the weight on the A, which will be 1, 1, 1, and 1. And then we'll have here the weights on the B, which will be the sine of 0, and the weight on the C, which will be the cosine of 0. Here we'll have the sine of 1 and the cosine of 1. Here we'll have the sine of 2 and the cosine of 2. Sine 3, cosine 3. And those will just be whatever they're going to equal. And then y will be, of course, the 1, 6, 4, and 7. And so we're just going to go through the same old process. The difference here is in the x. So x transpose x inverse x transpose y. And we will just, again, defer to our calculator, particularly in this one because of how messy the sines and cosines of things like 1 radian, 0, 2 radians, 3 radians, things like that will be. So what we just go through here is this. So clear that, and we'll just scroll up to whatever will be the most convenient one to change, and I think that one because it's got the right number of columns. So the first entry is always good, and then I just want sine 0. I'll put a decimal in there so that way it'll know that I want a decimal answer. So sine 0 and cosine 0. So I just wanted that one. Alright, so that ends the first row. Then we have sine 1 and cosine 1. I don't want it to give me crazy exact answers, that's why I'm putting these decimal points on there. We have sine 2. And cosine 2. And then the last one is going to be sine 3. And cosine 3. So I'm recycling as much as I can of the keystrokes to save myself all the trouble of entering it. And I get these things, and they're just crazy decimals, and there's nothing I can do about that. Okay, so is it right? Is it wrong? Probably it's right. Notice my calculator is in radians, which would have to be in this problem. Your calculator should basically always be in radians from pretty much now on in math classes. Not much cause for degrees in most cases. So then what we get is this, which we'll just round it, say round it to 2 decimal places will be fine. And here, so we'll get, I guess 3 decimal places, 3.912, 1.381, and then negative 1.959. So in other words, the model here that we would have is y hat is equal to, and then we would have 3.912 for the constant term plus a coefficient of 1.381 sine x minus 1.959 cosine x. Now, what do all of these look like? So we've now created 4 different models for this same data set. And so now let's have a look at what they each look like on Desmos. Alright, so what I have right here on Desmos, I have taken the liberty of already entering in the data values and then each of our 4 models. So these are our 4 data points. There they are. Okay, so first off, the regression line that went through them. Or it didn't go through them, but came as close as it could. So there's that line, and notice it is very close on that last value. That was when x equals 3, which we saw it was very close to that one. However, it was quite a bit further from the one where x equaled 1 or x equaled 2, or even when x equaled 0. So that's the line. It's the best line that we could fit through this data, according to the least squares way of measuring closeness. So that's the line that comes closest to fitting the data. But perhaps we don't want a line. Perhaps what we want is a quadratic. And so here would be the best fit quadratic for the data. And you'll notice that it has the characteristic quadratic shape. It's a parabola. And you'll also notice that it comes as close as any parabola could to passing through these points. It misses them, but not by much. And in fact, you'll notice it's closer then the line was the farthest that it ever is a little bit less than 2 off, it looks like, from each of these points, whereas the line was a little bit further off from some of them. So it's a bit better. But now let's look at the degree 3 polynomials. This is the cubic. Now this one was a case of polynomial interpolation. So it actually exactly fits through these 4 data points. Whenever we have a degree 3 polynomial with we can get an exact fit whenever we have 4 data points, as long as the x values are all distinct. If the x values are the same on any 2 of them and the y values are different, then that would be a case where no function could fit it exactly. You would just have to try to go through the 2 data points. So this is the cubic. But now let's suppose what we were talking about wasn't actually a polynomial at all, but because of some sort of external reason, maybe we're talking about something seasonal, or we're talking about the oscillations of a spring, or something along those lines. What we may have is something of a different stripe. And so perhaps we need it to be a trigonometric or a periodic type function. So this would be the trigonometric model that we found. So again, notice it doesn't necessarily fit the data so close, but it does the best it can for functions of this type. And if we were to change the type of the function, perhaps we could get a better fit. However, given what we did enter, considering that we didn't make any adjustment to the period or anything, it did the best that it possibly could for fitting this data, which was here. And if we had a periodically repeating process, then what would be going on here would be it's a little bit above and a little bit below the data, but we have a smoothed out version of it. So that's what each of these models would look like. And again, this case right here was a special case where we happened to have exactly as many data points as we had unknowns, and so it ended up being not an approximate model, but an exact model. Alright, so that's what that looks like. Now let's look at some more extensions of this into other terrains as well. Now the next extension of this is going to be what is called multiple regression. And the idea here is that y is a function of more than just one x coordinate. So there are multiple what are called explanatory variables, all feeding into the response variable. So the setup here, y is a function of x1, x2, up to some number of x's. Let's say xl. So then y hat or y equals, let's say beta naught plus beta 1 x1 plus dot 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 up to beta L XL. Or we might, if we're talking about specifically the 3-dimensional case, we might just say z is equal to beta naught plus beta 1 x plus beta 2 y. So this would be adapting ourselves to sort of the specific case of x, y, z coordinates, where we already have certain styles of writing things that we like. Other than that, though, nothing is really actually so different. So let's just go for an example, and you can see. So an example, find the plane of the form z equals beta naught plus beta 1 x plus beta 2 y that best fits. And then here we'd have some data set such as this 1 1 1 2 2 3 4 6 1 and then 2 3 5. Alright, so then let's think about this. So the parameter matrix or parameter vector, that is always going to just be our place to record what is up for grabs here, and that would be beta 1, beta 2, or beta naught, beta 1, beta 2. Now, the design matrix actually doesn't have anything very different in its setup from before. You just look at what the weights are of the different betas. So the weights here will be 1, 1, 1, 1. Here for beta 1 it'll be the x values 1, 2, 6, sorry, 1, 1, 2, 4, 1, 2, 4, and then 2. So these are the x values. Then the y values here, which would be 1, 3, 1, 5, because those are the weights on beta 1. And then we could say z for the z coordinate, which will be 1, 3, 1, 5. So that's the z coordinate. But nothing is different from how we would set this up. It will still be x transpose x inverse x transpose, not y now though, but z. So that's the only, sorry, that's z, not hat, just z the vector. Okay. So we would again just put this into a calculator and calculate away. Okay, here I go, entering in my design matrix. So 1, 1, 1. 1, 2, 3. 1, 4, 1. And lastly, 1, 2, 5. I'm going to store that under D again. I could have just scrolled up and, recycled some other one. But I thought that I'll just go ahead and enter this all fresh. Okay, now for my observation vector, it's going to be a 1. It's going to be a 3. So these are now just the z values. 1 and 5. Oops. 1, 3, 1, 5. Alright, so those are the z values, and I'm going to store those as O for observation vector. 1, 3, 1, 5, and then again, save me the trouble of having to scroll around and find transposes and such. I can just scroll up to here. Last time I entered this same old equation and find it and hit enter, and alright, I panicked there for a second because when I calculated that I got what I knew to be an absurd answer. And so now looking back at it, yep, sure enough, this is a case of last day jitters. I made a big blunder right here. I lost sight of which coordinate I was supposed to be looking at here. These are supposed to be the y values. So This should be 1, 2, 2. This should be 1, 4, 6. And this should be 1, 2, 3. So, whoops. And that led, of course, to an absurd answer, and because it was an absurd answer, I was able to catch myself. If the answer had been a little bit less absurd, I would have perhaps not caught it, and it would have been a catastrophe for the last lecture for this class to be on the record saying something so patently false. So what I did by accident was I lost track of which coordinate I was supposed to be dealing with. So we have a column of 1s automatically here to represent the constant term. These should be the x coordinates, these should be the y coordinates. So basically it should be 0, 1, 1, 0, 2, or 1, 1, 1, 1, 1, 2, 2, 1, 4, 6, 1, 2, 3. So oops. Alright, so fixing this now. So it should be 1, 2, 2. Probably some of you were pulling your hair out as I was writing it the first time. Oh well. That's what you get. And then, okay. So I have now made the necessary corrections. I fixed the entries that were wrong. There they are. Now fixed. Okay, now hopefully I can enter this. Oops. Enter this and get a more reasonable answer. Okay. Now that I like the look of. That other one I knew was not going to be accurate because I was implying that my model was going to be 0 plus 0 times x plus 1 times y, which is frankly absurd. 4 minus 2, 1. So then that means, oops, not y, really it's z here. So z, the projection of z, the least square solution for z, it's going to be 4 plus negative 2x plus 1y. Now if we had only had, keep on winning, my hand just wants to write the default, which is y, but here we are specifically talking about z's because we have a prior commitment to x, y, and z for the three coordinates in R3. Okay, so here, if this had only been 3 points, those of you who have taken some elements of vector calculus, either in 253 or maybe in 254, you'd have a different way of finding the equation of a plane that contains these 3 points. But if we have 4 points and they're not actually all on the same plane, which these ones weren't, then what that means is we can't find a plane that goes through them, but what we can find is the best fit plane that comes closest to going through them, and that's what we have here. All right, and now our last twist. A last twist on this. This is another example, and it comes to us from the subject of celestial mechanics, one of the oldest branches of all of science, the study of the motions of the heavens. And in particular here, this is based on Kepler's laws, in particular the first law. So the motion of a comet will satisfy, and then this is in suitable polar coordinates. R equals beta plus E times R cosine theta, where with R, this is the distance from the sun, and let's say that's in AU, so in astronomical units. And theta here will be the position in orbit. This is in radians. So then furthermore, then beta, so beta here, so the parameters will be beta this is the average distance from the sun, and then R, which is E, which is going to be the eccentricity. So the eccentricity of the orbit. So a higher value here means a more eccentric orbit, and a lower value means less eccentric. So then with E, there are these following facts. So if 0 is less than or equal to E, which is less than 1, that means the motion of the comet will be an ellipse. So this means will be an ellipse if E equals 1 exactly, the motion will be a parabola. And then finally, if E is greater than 1, the motion will be a hyperbola. So these are all examples of conic sections. So and actually technically if E equals 0, that would be a circle. That would just be a circle around the sun. So here we have a table. So we have a table of observed values. So okay, so you're some astronomer. You have discovered a comet, and you want to know what its orbit is. You want to see if it's going to hit the Earth, for example. So you make a little table of some of its values. You find the theta using all of your sophisticated equipment for measuring it relative to the sun. So say theta is 0.524, 0.785, and then 1.047. And then the R, which you maybe discover using parallax or something like that, would be 10.4, 8.7, and 7.1. So determine the type of motion and predict R when theta equals 1.2. Okay, well, we have to try to determine the type of motion and predict R when theta equals 1.2. So we have to figure out, is it an ellipse? Is it a parabola? Is it a hyperbola? What's it going to be? All right, well, let's think about the parameter. It's always easiest to start with the parameter vector. So the parameters here are beta and E. And this E is not Euler's E, not E like 2.7, but it's a number that's just going to be whatever it's going to be. Alright, and then x. So this is the design matrix. It will be 1, 1, and 1 for the values of the weights on beta in each case, and then here it's going to be equal to I might say just like r1 cosine theta 1, r2 cosine theta 2, and then r3 cosine theta 3. And then y here is going to just be equal to the r's. 10.4, 8.7, and 7.1. Where these are just coming from over here. And it's not worth our while to go around writing it all out, because it is, of course, the job of the calculator to calculate this. So we will just use it and sit back and enjoy a summertime drink while the calculator calculates away. So away it calculates, and alright, to save you the trouble of watching, I put all the stuff in for the design matrix, but made a mistake. Oh, this was supposed to be 1. Okay, so there's the design matrix. Alright, and then we just need the observation vector, and we are good. So, observation vector will be 10.4, 8.7, and 7.1. Store that. Your observation. Okay, and then we can just go back up wherever we last had this bit. Hit enter, and we get this. So we get 4.96 and 0.605, let's say. So this is 0.605. Alright, so the type of motion is, so E is equal to 0.605, which means ellipse. So it's an elliptical motion with an eccentricity of 0.6. And then as far as the predicted R, when theta equals 1.2, what we'll just do is calculate away. So R equals, so there's one little catch here, so 4.96 plus 0.605 times R times cosine of the 1.2. So the one little catch here is that R is actually on both sides of this equation, but that actually is not as that's not as tragic as it might seem. If we evaluate this and then we multiply those things together, we'll get 0.605 times cosine of 1.2. And this actually just gives us what is called a, I mean, it's just really what's technically just a linear equation. And so we get here that R equals 4.96 plus 0.219 R. Just multiplying those parts out. And so we can just move this to one side, so subtract that, and we'll have 0.6 781r equals 4.96, which means then that r is about equal to 0.96 divided by 0.781 is about 6.35. Astronomical units when theta equals 1.2. Alright, one note, so there's a similar problem like this in the Pearson homework. Make sure when you do it, your calculator is in radians. Other than that, you can just follow the steps that we've just done here, and you should be good. Alright, well that's going to do it for the official lectures of Math 261. So it's been a wild ride, and thank you for joining me. I'll see you next term for Math 256. Till then, bye.